Now, to finish up the subject of solving systems of differential equations, I would like to talk about how we solve systems using eigenvalues and eigenvectors. In particular, in the case that your eigenvalues and eigenvectors are complex. Now, let's see what happens. I'm going to state the theorem, first of all, and then we're going to see what it looks like to use that theorem in practice. Suppose you have a system of differential equations, homogeneous, constant coefficients, and you extract a matrix consisting just of the coefficients on x and y in the problem. Now, just like we did 2 days ago, we go into this matrix, we find its eigenvalues, and we discover that the eigenvalues are complex. Not real, but something of the form a plus bi, and its conjugate a minus bi. We found yesterday that if you have complex eigenvalues, they come in conjugate pairs, and so do the eigenvectors. You really can focus just on a single eigenvalue. You really can focus just on a single eigenvector. And so I will call that eigenvalue alpha plus bi, and I will call that eigenvector k. I'm going to denote by B1 the real part of the eigenvector, and I'm going to denote by B2 the imaginary part of the eigenvector. Then from this solo eigenvalue and its real part and its imaginary part, and from this solo eigenvalue, eigenvector and its real part and its imaginary part, then you can construct the solutions. The solutions satisfy the following equation. The solutions x of t, y of t are equal to C1 times the real part of your eigenvector times cosine of bt minus the imaginary part of your eigenvector times sine of bt, and that will be multiplied by an exponential e to the alpha t. And then C2 plus imaginary part times cosine of beta t plus real part times sine of beta t times exponential. Quite an incredible looking formula. Let's get some practice using this formula to solve systems of equations where the matrix has complex eigenvalues. For example, let's solve this system of differential equations. X prime equals negative 2x minus 7y. Y prime is equal to 1x and 2y. As always, I'm going to start by looking at this matrix containing the coefficients of x and y. And I'm going to find the eigenvalues of this matrix. Now, the eigenvalues of this matrix, something that we found in the previous video. We found that the eigenvalues of this matrix were lambda 1 is equal to plus root 3i, and then the other one was, of course, just the conjugate of that. We also found that the eigenvectors were given by the vector 1 in the first row and negative 2/7 minus root 3/7 I in the second entry. And the other one was just the conjugate of that. So I'm going to go in to these two sort of main values, this main eigenvalue, this main eigenvector, and I'm going to work on identifying what this theorem called alpha and beta and B1 and B2, and then all I have to do is slot those values into the correct places in this equation, and I will have solved the system. Now the value called alpha is the real part of the eigenvalue, and the one called beta is the imaginary part of the eigenvalue. In this particular problem, my eigenvalue has no real part, so alpha, as compared to the theorem, would be 0. Beta, as compared to the theorem, would be square root times 3. So these would be the values of alpha and beta that would go respectively into the exponential and into the trig part of our solutions. So that much is familiar, I think. That's very similar to when we were finding the values of r, when we were solving singular differential equations with constant coefficients. The real part went into the exponential, and the imaginary part went into the sine and cosine. It's very similar here. Now the B1 and B2 are equal to the real and imaginary part of the eigenvector. So B1 is what I get when I look in my vector and I extract all the numbers that are not attached to I. And B2 is what I get when I go into my eigenvector and I extract all the parts which are attached to I. So there are no i's in the top entry, but in the bottom entry, the number negative root 3 over 7 is attached to I. So now that I have my eigenvalues and eigenvectors, now that I've identified the real parts and the imaginary parts, all I have to do is assemble them according to the theorem, which says, hey, the solutions that you're looking for here, your x of t and your y of t, they are given by the following formulas. They are given by c1 times b1, this vector, according to the theorem cosine of beta times t, minus b2 times sine of beta times t, that quantity times exponential to the real part of your eigenvalue times t. So in our case, 0t. Then C2 will be multiplied by B2, which we identified as this vector, times cosine of root 3 times t, plus B1 times sine of root 3 times t times exponential. Now, if you wanted to, you could simplify and rewrite this, and you could find separate formulas for x and for y. For example, you could utilize the fact that e to the power 0 is equal to 1. And then you could look at what's happening in all these top entries. to say what is happening with x of t, which is in the top on the left side of the equation. X of t, for example, would be equal to c1 times 1 times cosine minus c1 times 0 times sine, so that vanishes, plus c2 times 0 times cosine, plus c2 times 1 times sine. Similarly, y could be found by looking at everything that's happening in these bottom entries. Y2 could be found by looking at c1 times negative 2/7 times cosine, then c1 minus negative root 3 over 7 times sine, then c2 times negative root 3 over 7 times cosine, and then c2 times 2/7 times sine. Let me show you another example of how I could use complex eigenvalues to solve a complicated system of equations. I have x prime equals to 5x plus y, and y prime equals to negative 2x plus 3y. If I look at the corresponding matrix, and I subtract lambda from the diagonal entries, and take the determinant, then I get 5 minus lambda, 3 minus lambda, plus 2, which looks like lambda squared minus 8 lambda plus 17. And using quadratic formula, that looks like 8 plus or minus the square root of 8 squared minus 4ac, which looks like 8 plus minus the square root of negative 4. So 8 plus minus 2i divided by 2. So 4 plus minus I. So my eigenvalues, of course, are conjugates of one another. So I'm going to focus only on one of those eigenvalues because the other one is sort of redundant. It can be gotten from the first one for free. Next, I'm going to work on finding the eigenvector corresponding to this eigenvalue. So from the matrix, I'm going to subtract 5 minus this eigenvalue, and then 1, negative 2, and then it was 3 minus this eigenvalue, which becomes 1 plus I, 1, negative 2, and negative 1 plus I. And I seek a vector which, when multiplied by this matrix, gives 0, 0. I'm focusing on the top entry. And if I look at that product, and I set V1 equal to 1, then V2 would have to be the negative version of 1 plus I to compensate. So the eigenvector corresponding to my eigenvalue would be 1 in the top and negative 1 minus I in the bottom. So now that I've found my eigenvalue and eigenvector for this problem, all I have to do is identify the values of alpha and beta and B1 and B2 in the theorem and assemble them into the formula and then I'm done. So alpha is the real part of lambda, the 4. That would be the part that goes with the exponential in the formula. Beta is the real part of the eigenvalue, that's 1. That's going to be the bit that is inside of sine and cosine. B1 is the real part of the eigenvector, the stuff that's not attached to I, so 1 and minus 1. B2 is this imaginary part of the vector, the stuff that is attached to I, so 0 and negative 1. And now my task is just to assemble that information into the formula in the theorem, and my work is done. So looking back at the theorem, we have C1 times B1 cosine of beta t, take away B2 sine of beta t times exponential alpha t, and then C2 B2 cosine beta t, B1 sine beta t exponential. Now you could, if you wanted to, you could go in here and extract individual formulas for x and for y, but there's not much need to do that unless the question specifically asks you to. So you're well within your rights to leave your final answer in this format as a vector equation. Now this is a situation where I think that solving by linear algebra is vastly, vastly superior to solving by the traditional method. If you're not used to finding eigenvalues and eigenvectors, this first step might feel a little strange. But compare that to what would be involved in solving this system using the traditional method. You would have to very, very carefully substitute one of these equations into the other. Then you would have to solve that equation. That would probably involve complex numbers as well. Then you would have to painstakingly take the derivative, which would probably involve product rule, and you would have to plug that into the other equation to finish the problem. So it would be a huge pain with lots of product and chain rule and many, many opportunities to make algebra mistakes. And this method, this linear algebra method, saves you a bit of that hassle.